Alright, good afternoon everyone. So today we are having a guest lecturer, so I can rest. So Rishikesh is here. Rishikesh Gajjala is a postdoctoral researcher at the Center for Quantum and Topological Systems at NYU, Abu Dhabi. He completed his PhD at IISc and got his bachelor's from IIT Delhi before that. His research interests broadly include quantum computing, graph theory, and combinatorics. He has published in leading venues such as Quantum, JCTA, Stock, and is also a recipient of the Quantum Graph Best Paper Award. His lecture is titled Quantum Photonic Experiments and Their Connection to Matching Theory. So I've known Rishikesh for a while now, right? So we met at FSTTCS, I guess, and then I was at IISc at some point visiting and giving a talk there. So I met with Sunil and Rishikesh over there. So it's really a pleasure having him here, and he's going to tell us how the theory of matching covered graphs could be used to solve some problems in quantum stuff that I do not understand. So we will try to understand that stuff, and feel free to use as much matching covered graphs terminology as you like. If we don't understand anything, we'll just tell you. Yeah. Okay. Over to you. Thank you.
It's audible.
Yeah.
Okay. So today we'll be talking about some quantum photonic experiments. So back in 70s, when they first found quantum entanglement, the quantum entanglement just means this. Let's say if you have two photons which are entangled, and you do some observation on the first photon, then the second photon, even though if it's far away, somehow what we observed in it, you can think of it as that message is passed to it almost instantaneously. It's faster than speed of light. It's not exactly that, but roughly this is what entanglement means. And the first thing physicists were trying to do was, can we improve this entanglement? Instead of having two particles which are entangled, can we have three particles which are entangled? So let's say initially the first particle had the spin to be either positive or negative. If you observe it and see that it's positive, almost instantaneously the other spin is forced to be positive. Earlier it was not known at all, but somehow it's immediately enforced. So they were trying to create three particle entangled systems and bigger things. And the three particle entangled state, it's written as a formula. This is called the ZHZ state. I'll tell you what this means. This just means what I said. Like, let's say if you observe the first particle to be 0, the other two are forced to be 0. Initially, it's a superposition of either all of them are zeros or all of them are ones. And whenever you just see one, the other things collapse to either all zeros or all ones. This is called a ZHZ state. And this is a ZHZ state in which there are three particles, and the dimension is, you can think of it as 0 or 1. You can also do 0, 1, 2, like two types of spins or any other mode number color, a lot of things. So ZHZ means Greenberger, Horn and Zeilinger. Zeilinger got the Nobel 3 years back for finding these ZHZ states, showing some properties about them and experimentally creating them. So a lot of these states, we know in theory they exist, but we don't know in practice if you can produce them. The hard part is, can you generate a general state? Let's say you have a ZHZ state, you want n particles with d dimension. So how does that look like? Let's say I want to write ZHZ 3, 3. That should be 0 plus 1 plus 2, and we just normalize it with 1 by 1. This you can roughly think of it as the square of this amplitude is the probability. So square of this is 1 by 3, each of these states happen with probability 1 by 3. And the square of the sums of amplitudes is always 1. Yeah, this is roughly the quantum background. And now they could create an experiment for 3, 2, and they could do some effort and create slightly bigger states, but they were finding it very hard to create a general template in quantum photonic experiments to create higher states. So they were trying a lot of possibilities. They were running a lot of, they don't just do every possible thing in practice, they just simulate a lot of things in computers. And they realized that a typical brute force search they are doing is not working. So they tried to formulate this problem in terms of just its mathematical essence. And in doing so, they came across some interesting matching theoretic stuff. And we'll see those. In the first 10 minutes, whenever I'm talking about the matching theory terms, I'll drop a reference to the quantum. But after 10 minutes, once you get an idea of what these roughly translate to quantum, I'll stick to the matching theory stuff. Okay. And there are other states. This is the DLB state. There is also the W state and the Dirac state. So what we'll do today is, first we'll start with a simple warm-up on why large dimensions are not possible in DLB states. We'll do this using some matching theoretic stuff. This is small puzzle-like matching theory problem so that you can get started in things. Then we'll get to the main problem of how big can W states be, how do you characterize them, and all these things. Let's start with the DLB states. So we are interested in the following graphs. We need edge colored graphs. These need not be proper colorings, any edge coloring, such that if you look at any perfect matching, it should be monochromatic. What is a monochromatic perfect matching? All edges in that perfect matching have same color. Let me draw an example. Draw this. Two perfect matchings and both are monochromatic. And you could just say that, okay, take any graph, color it with one color. Then of course all perfect matching should be monochromatic. So there is also one thing which prevents us from doing it. That's the second condition. For all colors, there exists a perfect matching which realizes it. So let's say if I say the color red, it means that there exists at least one perfect matching which would realize the color red. So for instance here, with blue you have perfect matching and orange you have perfect matching. And let's say I just draw this. Property 1 is still valid, but we also want that with the color yellow there needs to be a perfect matching. And this can easily be just cancelled out by saying that let's just look at matching covered graphs. So let's say if you are looking at matching covered graphs, if that edge is present, it would have been part of a perfect matching, and by 1 that would have been monochromatic. So yeah, that's it. So we'll just stick to matching covered graphs because the properties we are looking at are only about perfect matchings. So even if the graph is not a matching covered graph, just prune out all the edges, you are left with a matching covered graph, and then on that you can look for these properties.
So you want to maximize the number of colors, is it?
Correct.
Okay.
So we have a matching covered graph in which this property is satisfied. Then if you find an n vertex matching covered graph with t colors, then this translates to the VAG state with n particles and dimension d. So let's say if you want to create, if you look at this this graph, you have 4 vertices, 3 colors. So this corresponds to, and it satisfies this property. There are 3 perfect matchings in this graph, and all of them are monochromatic. So this satisfies this property and it's matching covered. So this should be CLC4,3. So since we are looking at perfect matchings, you will always end up creating only even number of particles. There is a small hack to just produce an extra odd particle. You can ignore that. So we'll stick to even vertices. Okay. So now we saw a simple example for 3 colors and 4 vertices. Can we get any? Okay, let's start with a simple example. Let's say if I have a graph with 10 colors satisfying this property, can I get a graph with 9 colors satisfying this property with the same number of vertices? Any ideas? Yeah. Either you can just take, let's say if you want to remove the color yellow here, you can color yellow as blue or just discard yellow. Either way, the property is satisfied. So if you have a higher number of colors, you can just get all possible colors lower. So instead of trying to look for color 5 or 6, let's start with a simple question. Can we have a 6 vertex graph with 3 colors? Let's try to construct and see.
Six vertex graph with 3 colors.
Yes. Let's start with 2 colors first. What can we do? Let's say if you want
Can you take an edge here and just subdivide it and get an example? Just subdivide it with 2 more vertices. Can we now make an example from that? Or?
No.
I don't know if it works in this.
Yeah. Now this subdivided edge has only 2 edges incident on it. So there are at most 2 perfect matches.
Can I add a parallel edge after doing the bisubdivision? Can I add a parallel edge?
Right. So first let's look at parallel edges. Can parallel edges be possible in this? So let's say if I have 2 edges like this, will it cause a problem to property 1?
Yeah. So they have to be the same color.
Correct.
Yeah.
So if they are of
then
different
the
colors.
issue again is so basically by subdividing and parallel edges.
Yeah.
Okay.
So whenever you have a orange edge, let's say you can take the orange perfect matching and replace this orange edge with a blue edge. Then property 1 fails.
Now we can, if we have a parallel edge, can subdivide both and add an edge this way. At least for cube.
Whenever you get a degree 2 vertex, you are forcing at most 2 perfect matchings. And because of that, you can't exceed 2 colors.
I'm saying you subdivide both and add an edge.
Add an edge between them.
For 3 colors,
It turns out it's not possible. Let's prove in general that it's not possible.
So 6 vertices is not possible.
Yeah, so the claim is that when your graph has, in general, this dimension you can get with this setup. There is a more general setup using complex numbers and other things, which we'll not get into today. In this simplification they had, for this property to hold, the best D you can achieve is 3, and the only way to achieve 3 is this, or an isomorphism of this.
Okay.
For any
only
other
K4.
Yes.
Okay.
And for any graph with at least 6 vertices, this D can't be more than 2. We'll look why the short. So let's first, we know that if you prove that there are no graphs with 3 colors, then that means there are no graphs with higher number of colors, because Srijit pointed earlier that you can just color one thing and keep doing that. So let's say we have three colors, orange, yellow and blue, and we'll try to construct a graph and prove that whenever we are trying to do that, we'll end up having a contradiction to property 1. So let's just start with orange and yellow first. There is an orange perfect matching and there is a yellow perfect matching. What should their union look like? Disjoint. So it should be a disjoint union of cycles.
It has to be only one cycle.
Correct. Because let's say if there are 2 cycles, just pick yellow from here, and from all other cycles, just pick the orange edges. So it should be one big Hamiltonian cycle. But this should also have a blue perfect matching. Let's try to slowly introduce a blue perfect matching in this and see why we can't.
Can you also put vertices?
Yes.
It's hard to distinguish orange and yellow. Actually, maybe you can put dots also.
Let's say I add a blue edge. Is this okay or is property 1 violated? I slowly want to introduce blue edges and at the end my goal is to create a perfect matching. So I just want to add one edge like this and see if property 1 is violated.
You have to add creating 2 odd cycles.
Correct.
Right? If you create even cycles, it's valid.
Correct. So whenever you take this, on the even cycle, you discard this and there is a yellow perfect matching because there is a path with even vertices and path with even vertices and you are done. You have a complete problem. So it should always create an odd cycle. So every outgoing edge from any edge from 1 should be instant on another vertex with same parity. Let's say 1, 5. And similarly 2 is matched only to even parity and so on. And let's say somehow all of that happened and there is a blue perfect matching in this. Now we want to say that whenever such a blue perfect matching exists, you can always end up getting a non-monochromatic perfect matching. That is what we plan to do. So among the all blue edges, let's associate a number to it where that number captures the number of vertices on the smaller side. So in this edge, there are 3 vertices here and 5 vertices on the other side. So this number associated to this edge is 3. Now there are a lot of blue edges because there is a perfect matching. Among all these edges, pick the edge with the smallest number associated to it. Let's say it's 3, this vertex. Now, in the smaller neighborhood, go to the immediate neighbor. This should have a blue vertex, blue edge. Can this match here? Because
It's potentially the smallest.
yeah, it contradicts them. So you know that this 2 matches to some other even parity vertex. Now look at this. These are 2 neighboring vertices. This is even and this is odd. So there are even number of vertices left here. There are even number of vertices left here. And even number of vertices left here.
So
Because the
is a
parity.
bisubdivision of K4.
Right.
Where 3 edges in a path have not been bisubdivided.
Correct. So the K for example is exactly when all these are 0. So we know that using this approach, using the unweighted simplification, it is not possible to create ZHZ states with at least 6 particles and more than 3 dimensions.
Wait. I didn't get the ending. So this much is fine. How did we finish?
Okay. So whenever n is greater than 6,
Yeah.
if there are at least 3 colors
Yeah.
and property 1 is satisfied, property 1 can't be satisfied. So with n equal to 6 and d equal to 3, there are no CSC states possible.
We're using the above diagram to get the perfect matching that is not multiple color.
Oh, we already got it.
Yeah.
Because you can just switch on that cycle.
Correct.
We have created. Okay. If any of those cycles is not C4, then you can just switch there.
Correct.
And now you have a perfect matching that's not.
Yeah.
So therefore it is K.
So for d equal to 3, we can't do n greater than or equal to 6, and because of that, we also can't have any n greater than or equal to 6 for d greater than or equal to 3. There is also something called uniquely edge colorable graphs. So a uniquely edge color, I'm telling you that there is a simpler proof if you use a complicated result from 70s by Thomason, using which you can prove that for n greater than or equal to 6, for any n, d is less than or equal to 3. We can't prove that, you can't just use it as a black box and say that with d equal to 3, K4 is the only possible graph. But you can conclude that you can't have graphs more than using something called uniquely edge colorable graphs. Now let's go to W-state graphs. That will be like main focus. This is just to get a bomb.
So when you say uniquely edge colorable graphs, you're referring to the usual edge coloring. Proper
Correct.
edge colorings.
Correct.
Okay.
So the thing with perfect matchings is, let's say if this property is satisfied, if a color has more than one perfect matching, you can just discard all the second, third perfect matchings. We just need to maintain one perfect matching. There is no advantage we are getting with 2 or more perfect matchings. So whatever answer you get is just a disjoint union of some k perfect matchings. Whenever you have a disjoint union of k perfect matchings, each vertex is k regular, and there is a unique way to k edge color it. That is by only coloring each perfect matching separately. So any graph with dimension d satisfying, if there exists any graph with dimension d satisfying this property, you can get a uniquely d edge colorable graph.
So that means that if d is equal to 3, then we are just talking about uniquely 3 edge colorable graphs.
Correct.
And uniquely 3 edge colorable graphs are actually exactly the Klee graphs, where you take K4 and you repeatedly replace a vertex by a triangle.
Correct.
Okay.
And the only uniquely k colorable graphs for k greater than or equal to 4 are the star graphs. Just color every edge separately, but those are not valid for us. Is that okay?
No, I didn't get the star graphs.
When you have a star graph,
What is the star graph? Just K1n.
yes, k1n.
Okay. Because it's not matching over, so I was confused.
Sorry, it doesn't fall in our example.
Okay.
But for Thomason's thing of uniquely k edge colorable,
Okay.
the only k edge colorable graph is when k is greater than 3 is a star graph,
I see.
and this doesn't have a perfect match. So there can't be any graphs with greater than 3 colors having this. But as Nishad said, even for uniquely 3 edge colorable, there is a complete characterization already. Then you can, on top of that, you can do some tricks, and you can see that only K4 is possible here. That connects to existing results. There's
I was just saying, in the characterization, we can use the characterization. If there's a non-trivial 3 cut, that is a cut which has 3 edges.
yeah.
There has to be a perfect matching that contains
Covers
all
all.
3 edges. Then you get a contour.
Right. Good. And you can also completely characterize when let's say you have, for any n, you have, let's say, d equal to 2, for which graphs can achieve 2 colors. You know that for cycles you can always get 2 colors, and it should always have a cycle 2, because we saw that the disjoint union is a Hamiltonian cycle. On top of that, you can see that there is more structure to it, and like there is a complete characterization of it if you're interested. Now we'll get to double state graphs. That will be like main focus. So each perfect matching earlier, when we were talking about the experiments, that corresponds to a measurement of the quantum variable on each vertex. Vertex is the number of particles. And if you take a perfect matching, in this measurement, each vertex is getting a half edge to it. This edge has 2 halves, and this half is saying what color this vertex gets, and this half is saying what color this vertex gets. And let's say if this yellow corresponds to the variable 0, then this means that this reading was 0, this reading was 0, this reading was 0, 0, and so on. And let's say if it was a different color, it's 1, 1, or whatever. Now, they could see that instead of this is their setup, so why do you have to stick to the usual edge coloring? Why can't we just have an edge in which each half has a different color? This notion of half edge coloring, every half edge getting a color, helps us capture a much more richer class of graphs, and that is very useful for our W state graphs. These things are not useful in the CH3 state. Can you think why? Let's say if this edge is part of some perfect matching, then that is not monochromatic. Everything should get the same color in CH3. So that's useless for us. So their multi-edges didn't have much purpose, and this mixed colored edges also didn't have much purpose. But both of them turn out very necessary for W state graphs, both multi-edges and these mixed edges. So now we are in the...
Instead of a half edge coloring, you can also view it.
Subdivided.
Every edge has 2 incidences. One with...
Correct.
There are 2 ends of an edge. I'm assuming you're not allowing loops.
Yeah.
So therefore every edge has exactly 2 ends. And instead of half coloring the edge, I can also just think of coloring each incidence of that edge. The incidence with U,
Correct.
the incidence with V, where E
Right.
is my edge U.
Yes. Okay. Now let's see what W state looks like in the quantum terms. This is the W state graph with 3 particles. It's basically, and you need to normalize it. It's basically saying that take all the Hamming width 1 strings and consider their superposition. So you have 3 particles. So first was 0, second is 1, second is 1, rest are 0, first is 1 and rest is 0. These are the 3 possible Hamming weight 1 strings. If there is n, you can see that there are n such strings with normalization 1 by root n. These are called the W states.
Here there is no dimension. It's always
No, there is no dimension. We are just interested in number of particles. There is no dimension. So now you can see there is only one half edge which is coming out to color 1, and all other half edges are 0. That's the reason half edge coloring becomes sort of necessary. Let's see an example. Let me just state what this means in the graph theoretic thing first, so that it's easier. The first property is this. For all perfect matchings, if you are given a perfect matching, you can break it into n half edges, depending on which vertex the half edge is incident. Basically, n by 2 edges are there, split each edge into 2 more half edges. For every perfect matching, you have one red half edge, and n minus 1 blue half edges. And the second property is this. The first property says that all perfect matchings fall into one of these. Is that okay? And the second property says that for each of this, there exists some perfect matching which realizes it. For all vertices, let's say pick a vertex V. V has half red incident on it, and the remaining vertices, n minus 1 vertices, are blue.
Is this some perfect matching for which this happens?
Yes. I'll draw a small example so that it's. Let's take 4 vertices.
Label the vertices.
Yeah, it's very important to label here because of half edges.
Next.
So, let's see why this is a 4 vertex double state graph. Let's see the first property. For the first property, we need to check that in every perfect matching, there is one half red edge and everything else is blue. So let's look at the horizontal perfect matchings first. This is blue. You pick either of these, there is a half blue, half red. So one is good. The vertical is correct. Cross edges, it's correct. So property 1 is satisfied. Let's say I want to turn one red. I could pick this perfect matching with this edge and the blue edge. In this perfect matching, one is turned red.
So now you are checking the second property.
Yes.
Okay. Can you repeat that one?
For the second property, we need to check for each vertex. There exists a realization where half edge is incident on that vertex. So we'll do a 1 by 1 check on all 4 vertices. Or an easier thing to do is this. Let's say if each of the vertex has a half red edge incident on it.
Yeah.
Then we are done because it's matching covered graph and there would be some perfect matching.
Yeah.
Because property 1 is satisfied. So you have.
Yeah, because for every perfect matching, you anyways know that it will be half red edge and everything else will be blue.
Yes.
Yeah. Yeah. Okay.
So you can think of it in a much easier way now. Think of only matching covered graphs.
The colors are not symmetric, so red is different from blue here.
Yeah.
Yes.
Yeah.
There is an asymmetry.
Yeah.
Because we now understand this, there is an easier way to put this out. Let's start with a matching covered graph. First thing is that for every perfect matching, there should be n by 2 minus 1 blue edges and 1 mixed edge.
Yeah.
Because the only way you get this is if there are n by 2 minus 1 blue edges and 1 mixed edge. So this is the structure of all perfect matches. N by 2 minus 1 blue edges, 1 mixed edge. And the second property says that for every vertex, there should be at least one mixed edge incident on it with the red part on it,
Yeah.
not just anyway. If it is anyway, then this
Every
coloring
vertex should see the color red. Is that? But that's not enough, is it?
What?
Every vertex should see the color red. Is that enough?
Yes,
That's
that's
enough,
enough.
right?
Yes.
Because if it sees the color red, it
will-
sees it because of a half edge incident at it, which
Correct.
is colored red. Anyways, you can't have full red edges.
Exactly. So let's prune that out. Let's say if there exists an edge which is fully red, then it is part of some perfect matching because we are dealing with matching covered and property one
Property
fails.
one as well.
So you have only blue edges and mixed edges, and these mixed edges are sort of sparse. So another way to think is, let's say you have
They're not sparse in the example. Okay, the example is small.
okay. Basically, you just need degree 1 on each vertex.
Yeah.
Yeah, the example itself is too small.
Yeah.
Six, it has how many?
It has 4 vertices.
It has 7 edges in total. Right?
Yeah. Now let's try to construct a generic example with n vertices, and then try to characterize it.
So are there bipartite graphs with this property? Or is bipartite like very small set?
I think there are no bipartite.
Right.
Yeah. No simple proof I can think of, but okay. So let's try to construct a simple example. What if you look at all the set of red edges? In some sense, it resembles a tight cut because all these red edges should be part of exactly the set of mixed edges. Let's say this set S. Pick any edge in this set. This is part of exactly one perfect matching. So this S, where set is S is the set of all mixed edges. Intersection any perfect matching has size exactly 1. But this need not be a cut. This could be very arbitrary. So if you think of tight cut in a more general way, that it is a set of edges which intersects each perfect matching exactly once, this is satisfying that property. So since we saw this, let's try to force it to the simplest case and try to construct an example with it. This says that it's more general than tight cut. That doesn't prevent us from forcing it to be a tight cut. We can create an example with the tight cut, and the most easiest thing you can do is make it a trivial tight cut. So let's just make all this S incident on one vertex and try to make an example out of it. Is that okay? So label.
So you will make all the mixed edges incident at one vertex.
Yes.
But the second condition requires that every vertex has a mixed edge incident at it.
Right. So I'll force this incidence using multi edges, which gives. So let's just see. So let's say if these are the vertices. First, I need to force 2 to get the color red. So I'll just put a red one. And do this. I want to force 3 to get red. I'll do the same thing. So on, I'll do it for all vertices. We made it happen for all vertices, but this vertex is not getting red. And since there are all these edges, the only way to do is put a multi-edge. And multi-edges here are not a problem because if this is part of a perfect matching and you replace this edge with this edge in that perfect matching, property 2 is still satisfied because you are just switching. So there can't be multi-edges like this because then the number of blue halves will get increased.
So all multi-edges have to be mixed edges.
Correct.
Can you have two non-mixed edges that are multi-edges?
Two non-mixed.
No.
The only non-mixed are blue. So
Right.
since we proved there are no red,
Right.
putting 2 blue is same as putting 1 blue. Like there is no difference.
Okay.
So now we made property 2 happen here, but still we don't have property 1. We need to get a perfect matching for all these vertices. Can you connect it with some concept you know? You want this edge to be part of a perfect matching. So you have these n-1 vertices. You remove this, there is a perfect matching here. You remove this, there is a perfect matching here, and so on.
To make a wheel.
Yeah.
That's what you want to do?
Or any factor critical graph.
Let's
So
make a wheel.
remove, that's the simplest, yeah.
Jesus.
Pick any vertex, remove it, you need a perfect matching on the remaining thing. So I can just take a factor critical graph here.
Any factor critical graph will work.
Yeah.
Yeah.
Is that okay? Now we saw property 1 is satisfied. Let's check for property 2 in this.
So edges will be blue in the factor.
Yes.
Yes.
Sorry.
Blue factor.
So for property 2, when you want this to be red, match this. This is a factor critical graph. Remove vertex 2, you have perfect matching, and so on. And to get this, just take the red incident on this, and you have that. And you can make it the smallest factor critical to get a small graph. It's odd second. If it's odd, if it's even, I don't know. What is the answer if it's?
If it's even,
If it's even, it's not factor critical. So we need the total graph to be even. You remove one vertex. This is all. So the smallest graph is an odd cycle, but in general, any factor critical graph. Actually, it's a little more specific than factor critical. It is factor critical in which every edge is part of this global perfect matching. There could be a factor critical graph in which some edge is not participating any maximum, any n-1/2 matching, right? So consider some factor critical graph. There could be some edge. That edge could not be participating in any of the maximum matches.
So I have a question related to what you're saying. If I take a factor critical graph and I add a universal vertex,
Yes.
because your one
Yeah,
universal
that
vertex.
is a universal vertex.
So if I take a factor critical graph and I add a new vertex and I make it universal,
Right. We want this to be matching
is that
covered.
matching covered?
No.
No, right? Can you make a small example? Maybe if you take two triangles in meeting at one vertex, two triangles meeting at one vertex,
Tension.
and now add a universal vertex. Is that matching covered?
I think so.
Maybe it is. Can we try?
It is not if you do this.
Is this matching covered?
Yeah, it is. So these two are part of one perfect matching by taking this.
Yeah.
This and this are part of a perfect matching. This and this are part of a perfect matching. Similarly, you can do this. But there are examples where you can have a factor critical graph when you do this,
Which
it is.
graph is this? Which graph is this? Is this T6 plus 1h? Santosh?
Yes.
This is T6 plus 1h, right? Yeah. Sorry, so T6 is the following graph. You can draw two vertices, one on the top, one on the bottom. Put two K2s sleeping, one on the left side, one on the right side. Join the top and bottom vertices to all the four vertices of the K2s. And now join the top and the bottom vertices with an edge, and that's your graph.
Okay.
So the general question
There are two
is,
universal vertices here. Right?
here there are two vertices that are universal.
Here there is only one.
Here also there are two.
No.
The middle one. The intersection of the
Oh, the intersection
That
is
is
also
universal.
universal. Yeah. Okay.
Yeah, this is the same.
Yeah, it's the same.
So the question again is, if you take a factor critical graph and you add a universal vertex, is the result matching over or not?
No, it's not. It need not be.
Okay. Can we make a small example?
Let's take. I don't have anything handy. We can try it.
Try it.
So now everything is part of a perfect matching in this. Maximum matching in this.
Yeah.
Now I want to introduce an edge which is not part of any maximum matching. This is. Let's make it 7 vertices. Is this part of a maximum matching?
So,
Oh, it is, right?
The factor critical graph you are taking, if it is Hamiltonian, then you won't get a counterexample. Because if it is Hamiltonian, then the result you will get will be a supergraph of a wheel.
Right.
And that will be matching covered because brick plus
okay.
any number of edges is a brick.
Right.
Right? So the factor critical, that is one of the reasons I suggested taking two triangles sticking at a vertex,
Sticking
because
at-
that fellow is not Hamiltonian.
Right.
So you'll have to take something that is not Hamiltonian.
Right.
One thing we could try is we could take this one step further. Can you take three triangles sticking at a vertex? Does that fellow now add a universal vertex? Does this work?
Oh yeah, this is just
It's the same thing, right? Is this a family? Okay, I see. So this,
Yeah.
what they are saying is this will also not work.
Yeah.
But so let's say there is an edge that of a factor critical graph that does not belong to a perfect match, near perfect match.
Then we are done.
Then we can get a vertex set, like something similar to a valley. Then I feel we could arrive at a contradiction.
Yeah, that's what I.
Oh, I don't have any example, so maybe it is that like. I thought it should be the case. Like, why not? But
Okay. Anyways, we can think about it later.
yeah, interesting question.
So put it as DIY on the answer. Let's draft the counter example or prove this.
Okay. So we have a small example here for any n vertices. You have this example. This is called, let's call this a W cone. It's like a cone. Now we are interested in characterizing all possible W states. We want to say like what should their structure look. We saw some specific examples, but we don't know what a general W state graph look. Or even think of it algorithmically, like let's say the physicists have an uncolored graph. So that is equivalent to having an experiment in which their mode numbers are not fixed. And they need to find the right set of mode numbers so that these experiments give a valid W state. That is equivalent to you are given an uncolored graph. What's the best way to color it? So that, or is it possible to color it to achieve a W state graph? Let's start with a simpler question. Let's say if someone gives you a W state graph Can you verify it in polytype? You are given edge colored graph. I want to verify whether it's a W state or not. First,
So
you
the
can,
second property is easy, right?
right.
Each vertex is a red color. That is easy.
Right. First, do the matching covered pruning,
Yeah.
and second property is easy. Just red degree is at least 1. Now we need the first property.
So that just means that you don't want two mixed edges to belong to a perfect matching.
Exactly.
That I can do. I'll check all possible pair of
Enumerate.
non-edges and mixed edges.
Correct. So second property is trivial. For the first property, when does this property fail? There are two cases. Either there exists a perfect matching in which everything is a blue edge, or there exists a perfect matching in which at least two edges are mixed edges. In the first case, discard all mixed edges. You have a complete blue graph. In this blue graph, check whether there is a perfect matching or not. If there is a perfect matching, you are done. Otherwise, even in the original graph, there exists no perfect matching. And for the second side, instead of checking 2, 3 everything, you can just pick 2 mixed edges. All, let's say if there are alpha mixed edges, you pick all alpha choose 2 pairs. Now remove these 4 vertices, and on the remaining n-4 vertices, run your perfect matching algorithm and see if there is a perfect matching. Any perfect matching here violates the condition. This n-4 vertex graph, you include the mixed edges also, because there could be 3 mixed edges, 4 mixed edges. Yeah, that's a simple verification algorithm for this. But we are interested in the more general algorithm of like you are given uncolored, can you color them in the right way? Even that becomes clear once you know the structure of these double state graphs. And the structure turns out to be the following. We'll see how it happens. If you take the graph and decompose it into 3 connected components, each 3 connected component is a double equal. You might need to add some mixed edges when you are doing the decomposition, some small intricacy, but on a high level, if you are given any double state graph, you can find out its unique 3 connected components, and all these 3 connected components are double equals.
And by 3 connected components, are you referring to what, for example, is explained in Quanti-Murti? Like you take 2 vertex cuts,
Yeah, correct.
you get the 2 smaller marked components, and you keep doing this.
Right.
And here are we assuming our graph is matching covered?
Yes. Because for these properties we
So then the 3 connected components need not be matching covered, right?
yes, that's the reason I said when you are doing this decomposition, sometimes you might need to add an edge on the cut vertices.
Nice.
Let's say you are picking a 2 cut vertex and getting, let's say if this was the earlier graph, you decompose it into 2 parts. Second is this. Sometimes you may need to add an edge.
But if the 2 components have even number of vertices,
Right.
then it's good. But if both components have odd number of vertices,
It turns out they never have in this graph.
Oh,
Because of the way double state graph is.
oh, I see.
All of these.
So you are saying that all your 2 vertex cuts, all the components after deleting the 2 vertices are actually even,
Yeah.
even order.
Yes. So we also have an intermediate step to get this result, that whenever you take a 2 vertex cut and do this decomposition, these 2 things are again double state graphs. So once you prove that, it's just recursively repeating that
And
line.
this is if and only if. This
And-
is W state if and only if both of those are W state.
Correct.
That's if and only.
There could be multiple.
Yeah.
And once we get this, it's easy to get this, that you keep decomposing and you can prove this. Now, instead of directly trying to jump there, let's try to see some nice structure about double state graph so that we are set up to prove that. this board, is it visible? In the camera it is. So
all these graphs are then bicritic.
correct. There?
They're all bicritical,
Yeah.
but not necessarily bricks.
We'll prove that.
They're bricks.
They are not bricks and they are bicritical, so they should have a two vertex cut.
Right. Okay, so they are bicritical, but not necessarily. In fact, they are not bricks.
We'll prove that they are not bricks.
Oh.
And hence you'll always find a two vertex cut. And then we'll do this. Okay. So before we get into the general, the entire W state graph, let's look at just the blue edges and figure out their structure first. Then we'll try to put in the mixed edges and see how they look like. Is that okay? So the blue edges could be like, there are a lot of near perfect matchings. You just have to leave out one edge. There could be a lot of stuff could be happening. It's not clear how they look like. But you know this property, we know this property that pick any vertex, then it would have had a mixed edge on it before removal. Let's say it was there to some other vertex here. And the remaining there would have been a blue matching. And this is a missing edge. So the vertex 1 and 2 are inessential. If a vertex is not covered by at least one maximum matching, we can say that that vertex is inessential. So the vertex 1 and 2 here are inessential.
In the blue graph.
Yes, in the only blue graph. We'll just see the structure of only blue graph. And since every vertex would have had a mixed edge incident on it, all vertices are inessential in the only blue graph. And if all the vertices are inessential, it should be a union of factor critical graphs. You can go to the Edmonds-Gallai theorem and plug in these, and you get that.
So we don't know if it is connected.
Correct.
Okay.
The entire graph is connected, but maybe the blue parts are disconnected.
The blue subgraph may not be connected.
Correct.
Yes.
You have some factor critical parts. And since the total number of vertices is even, you know at least two of them are present. Two components are present. It's not connected. If it was connected, like there would be one factor critical graph, number of vertices is odd, and the number of vertices in this graph is same as this. So contradiction. That should
So
be.
you have an even number of components.
Correct. And we'll prove that it's not any even, it's just 2.
Okay.
Why is it the case? Like, let's say from this vertex, there is a mixed edge somewhere here. This should have a, if you remove these mixed edges, it should have had a blue perfect matching, but now it won't have a blue perfect matching. So there can't be more than 2 components. And all these mixed edges should not be in the same component. They should be start from one place and end at another. Because if that doesn't happen, again, you can't have a all blue perfect matching. Is that okay? So your graph is this. What were you hoping for in the start? You're hoping whether this could be a tight cut, and we proved exactly that this S is a tight cut between two factor critical points. So has a tight cut. And our goal is to get a two vertex cut, and it has a tight cut, so we just need to prove that it is not bicritical.
It is like
Sorry, it is bicritical. Is that okay? So let's go back to this graph. Remove a vertex here and a vertex here. This is factor critical. This is factor critical. So now you have perfect matching, even without using the mixed edges. So when you pick two vertices on the other sides, you are done. But both of them could be on the same side. We'll prove that even if they're on the same side, if you remove them, you can get a perfect match. Let's say I remove these two vertices, 1 and 2. Consider the perfect maximum matching in this when you remove the vertex one. Since this is factor critical, there will all, if you remove one, everything else is covered. So let's say 2 is mapped to something. I'm just picking any two arbitrary vertices first, and within those two I'll pick one arbitrarily, and 3 is defined as the vertex to which 2 is matched. Consider the perfect matching, in which you are taking the mixed edge from 1, 1 prime. Let's label that PM1. Is that okay?
Either of the 1 and 1 prime can be red or
Yes. The color is not important. It's just a mixed edge. So this is the perfect matching one. Now I want to do some tweaks to this perfect matching and get a perfect matching in which 1 and 2 are not present on this graph. On the entire graph, sorry. Is there any?
Oh, I see. Can you use an assignment problem?
Yeah, so there was this assignment problem that if the graph is a matching over any multiple, and if the shown on the one side is critical, then you take the cut contraction of this, and that is bicritical.
Oh, I see. If any shore,
the big graph itself is bicritical. Yeah.
There might be options.
G itself is bicritical. Vertex is contraction in the market. Then yeah. That was the show.
So we need to prove this. Okay. First we consider the following perfect matching. X1 is mapped to some 1 prime, the vertex 1 prime. And let's say it's PM1. Now I'll slowly tweak this to get a perfect matching in which the vertices 1 and 2 are removed. Okay. So when X1 was mapped, when the vertex 1 was mapped here, 2 was mapped, had an edge to 3. 3 is defined that way. Now, three would have had some mixed edge to another vertex here. Okay.
And if you shrink the other side, now we have because this shrunken vertex is universal. Right. Is it universal? Yeah, because every vertex has a half color.
Oh. So if you shrink the right hand side into a single vertex,
Yes.
is
It
that
is
vertex
universal.
universal?
Yes.
Okay, go ahead.
So factor critical graph plus a universal vertex should be bicritical.
Is bicritical. Factor critical plus universal is bicritical. Is that true? If I have a factor critical graph and I add a universal vertex.
We are not even sure if it's matching covered.
Oh, right.
Yeah.
You couldn't even answer that. Maybe you should answer the stronger question.
Factor critical just means if you delete any vertex.
So if you remove this vertex, it's easy. The main
Oh, yeah.
that we saw here too. But if you remove two vertices on the same side, that is when we are running into them.
Actually, that's not immediately critical. This side is 2%.
This side is 2 connected, one side. No, I don't think any side is 2 connected.
No, it's not.
No. Just factor critical.
Yeah.
We don't know if it is 2 connected
No.
factor critical. Yeah.
Actually, we'll get to that too. Two connectivity. If it was two connected, it would have been done much easier in
Right.
between. When it's not two connected, it gets messy.
Okay, go ahead.
Okay. So first, I take the perfect matching 1 with the edge 1 1 prime. Now, in that perfect matching, there would have been this edge 2 3. Now I'm creating a new perfect matching the
Can
following.
you color those two edges with one more color? Maybe yellow or something. No, not green. Yellow. Not green, not green. Good. Yeah, those two edges you mentioned, 1 1 prime and 2 3. You could just color them yellow. And that one also, right? The first one, the top one.
It's top one.
Is it the same perfect matching or is it not?
Same perfect match.
Both of them belong to the same perfect matching.
Correct.
Okay. Now what's your next perfect matching?
Consider the perfect matching. Okay. From this perfect matching, discard this edge. Discard this edge. And map this with this.
Okay, so you're removing two edges and you're including another edge.
Correct.
Okay.
Now this side is factor critical, so this can be matched. So all of this would have a perfect matching. And here, since you removed the x1, x2, x3, x1 prime neighbors, all the other vertices are mapped or matched with the yellow. So the remaining yellow plus x2, x3, sorry, plus x3, 3 prime and the factor critical stuff here, they form a perfect matching in which x1, x2 are missing. So in other words, we know that there was a perfect matching initially just here on this part, by removing x1 and on all other vertices. In this perfect matching, just on this side, I'm removing this edge, yellow edge too. Now I have a matching which covers everything except x1, x2, x3. If I just cover x3 now, I'm done for this part. For covering x3, I'm taking the mixed edge here, and then I use factor criticality. So if you remove any two vertices, you are done.
Okay.
Is it clear?
So just to repeat, you took a perfect matching after deleting x1
Yes.
in the left hand side. Now, because it is a perfect matching of the left hand side minus x1, x2 fellow, who is the other arbitrary vertex you chose, is matched to somebody, say x3.
Right.
Okay. So now what you are doing is, but you want to have x1 and x2 to be exposed, the only two exposed vertices.
Right.
x3 has a neighbor on the other side, the right hand side.
Right.
So you will take that edge.
Right.
And now you will delete the neighbor on the right hand side. Factor criticality, you'll get a perfect matching there.
Correct.
So now what you have is something that covers everybody except x1 and x2.
Right.
Okay.
Okay. So now we proved it's bicritical, and we knew it had a tight cut. So there should be a two vertex cut. By what? It's ELP here.
Yeah. Yes.
For YouTube, for people who don't know.
Yes. ELP 82. One small point.
Yeah.
These left and right are both factor critical.
Right.
Right? These are the graphs formed by the blue edges.
Correct.
And there can't be an isolated vertex here because every vertex is incident with at least one blue edge, because every vertex has only one mixed edge. Therefore, the other edges are blue edges. I'm just worried that these should not be trivial.
They can be
Left and
trivial.
right,
They can. And when it's trivial, it becomes this.
they can be trivial.
Yeah, sorry. Right.
And the
sorry.
trivial case is that case.
Correct. Sorry, my bad. This tight cut is when
Okay,
either
it may or
X-
may not be trivial. Trivial case you're already done there.
Correct.
Okay. So it has to be non-trivial, therefore there is a two separation.
So when one of these is at least 3, we have this. When one of them is 1,
Yeah.
we have that to be exactly this. One of this is 1. So all the it is factor critical, and all the outgoing edges from this one vertex should cause this. Sorry.
So these are the ones that have a universal vertex.
Correct.
The other ones actually won't have a universal vertex, no? Or they could also have.
They could have universal this side with mixed edges, and within this side they could have blue edges making them.
In fact, if you have a two separation cut, then the only universal vertices are those two vertices, possibly.
When
Nobody
they are
else
two
can be
connected.
traced. Sorry?
When they are two connected, these parts. Otherwise, they could disconnect these parts. If there is
If
universal,
there is a two separation cut,
yeah,
then I am claiming that all the universal vertices have to be amongst
Correct.
those two. Of
Right.
course, it could be 0.
yeah,
Right.
correct.
Okay.
And that's what we are getting to. Okay, we proved that there exists a two vertex cut. First, the two vertex cut need not be one vertex here, one vertex here. Maybe the two vertices are here. That is not possible. Let's say you remove these two vertices. Can it disconnect the graph? This side is connected. This side could be broken into many parts. But you know that every vertex here have a mixed edge going here.
Yeah.
So all of it is connected because of this connected bond. So these two vertex cut should have one vertex here, one vertex here. So let's say this is the two vertex cut. Let's look at the simpler case he suggested earlier. Let's say this is two connected. That is, V is not a cut vertex. You don't need to be two connected. Let's say this is not a cut vertex and this is not a cut vertex. Is that okay?
That means that all the edges of this cut are incident with V or V prime.
Correct.
Is that right?
So there are all these mixed edges from here coming. All of them, when you remove this vertex, let's say if all of them are not coming here, or all of these are not going there. This part is connected by assumption because it's not a cut vertex. This part is connected. So consider the remaining graph below this line, except for these. Even if there is one edge between them, then it's connected. And all the mixed edges are between these. So the only way for this to happen is all these mixed edges go here and all these mixed edges go here.
Yeah.
Is that okay? Now let's see what's happening if you remove these two vertices. If you remove these two vertices and discard this part, this along with this forms a W cone. And that vertex along with this part forms another W. So if you take two W cones, select an arbitrary bicolored edge. Based on this, add a different W cone like this based on this vertex and this. This becomes exactly this.
So your graphs are bicritical.
Yes.
And they are not bricks.
Correct.
However, for a bicritical graph, the tight cut decomposition will give you only bricks. You will never get braces.
Right.
In fact, you can prove that a matching theory graph is bicritical if and only if the tight cut decomposition produces zero braces.
Yes.
And only bricks.
Right.
So my question is there a bound on the number of bricks? Are your graphs, is it true that they are bricks, number of bricks is equal to 2?
No, they could
No,
have more.
they could have more bricks, right?
Repeatedly do this
You can repeatedly
decomposition.
do this.
Get a lot of bricks.
Okay. there
So
is no
this is
bound.
the simplest case in which these are two connected.
Uh-huh.
But it could be the case that when you remove this vertex or this vertex, this part could break into multiple small pieces, and all of those could have weird interactions.
Yes.
Standing weird. So that proof is a little sophisticated. I mean, but there are better things to discuss on that. So we'll skip that. But the general idea is this: we identified the two vertex cut. Here you could see that if you remove this, you could decompose it into the first W cone like this and the second W cone like this. When you remove a cut, if this was a cut vertex and you remove this, there are multiple components, and you can prove that each component plus this along with this graph, that is again a W-shaped graph. And you can do this recursively and break it, and you'll get a W cone in the end. Every time this falls below 3, and eventually you can prove that you'll be left with only W cones. Because if you're left with any other graph, you could have done one more decomposition and got a smaller graph. And you can prove the opposite too. Whenever you paste things over a micromatic, you can construct the original graph. So it's a complete characterization. Okay. So
And the W cones themselves are bricks, right?
W cones themselves are depends on can factor critical.
Yeah.
The structure is this, like you have one universal vertex and a factor
But if
critical.
it is not a brick, it is still bicritical, is it?
No, that was the question he asked.
Oh.
I don't know.
That-
So
the
here
critical
there is
plus
nothing-
Universal vertex is bicritical, is that true?
Yeah.
Factor critical plus universal vertex. If I delete the universal vertex and somebody here, then clearly you are fine. What about if I delete two vertices here?
I was trying to think in terms of barriers. There is a barrier.
First is matching covered, right? We had to prove
Yeah,
that.
we didn't even prove it as
Yeah,
matching
yeah.
cover. Right.
And I was thinking, for factor critical graphs, we have, if you delete a set of vertices, the number of our components is bounded. And similar thing goes for bicritical.
Well, it intuitively seems like there should be something, right? Because your final graphs are bicritical.
Yeah.
And you are saying that you are recursively breaking down into smaller graphs.
And we are breaking using only these mixed edges.
Right, but you're using these two vertex cuts
Yes.
to break them down.
Correct.
In a bicritical graph, if you have a two vertex cut, let's say UV is a two vertex cut,
Right.
let's say G is your bicritical graph,
Hmm.
then G minus U minus V will have only even components,
Correct.
right? Now what you can do is you can take any even component. This is similar to your three connected thing that you talked
Yeah.
about, right? You can take any even component, let's say K, and look at the subgraph induced by K union UV, vertex set
Right.
of K union UV, and now add a new edge joining U and V, right? This is actually going to be again a bicritical graph.
Right.
If you add an
Yeah.
edge joining U and V. If
Right.
you don't add a new edge joining U and V, then I
You don't.
cannot say this.
Yeah.
But if you add one edge joining U and V, then this is again a bicritical
Correct.
graph. So for every even component, I will get these graphs, and if I keep doing this, in the end I will just get bricks.
Right.
So that is why it seems the way you are explaining, you have this bicritical graph, and you are getting these smaller graphs from that,
Right.
and you are saying that you will get a recursive thing.
And by
In the
adding
end-
edges like you're saying.
Yeah, in the end, what you should get should be a brick.
Right.
And your W cones seem to be the case where you don't break down any further.
Right.
So intuitively, all of this suggests that W cones should be bricks.
Yes.
So it would be really nice if you could come up with an example of a W cone.
Yeah.
Is it cone or core?
Cone.
Right? Yeah. If you could come up with a W cone that is not a brick.
Right.
Factor critical plus universal vertex is
Yeah. That is what W cone is basically.
That is bicritical.
Is it?
Yeah, because if not, there is an outer barrier,
Yeah.
and the barrier must contain the universal vertex.
Yes.
Oh wait, I'm missing a border case. I think probably. Yeah, this barrier can have size at most 2 is what I can see. I thought there's because if the barrier is larger,
Then you can delete two other vertices. Oh, I see.
if the barrier is larger, you forget about the contraction or the universal vertex. And now we have at least 2 vertices and many odd components. So removing one vertex will tell you that there is no near product. So yeah, then you can say every.
By the way, just a quick note. We are at 4:45.
Yeah, I did
This
tell
room
you.
is booked at 5 o'clock.
Yeah.
Another alternative is I have booked another room.
Oh.
So if you would like to not stress out and rush, we could take a break here and go to the other room
Okay.
and continue there.
Yeah.
If you want to finish in 10 minutes, please go ahead. Up to you. Yeah.
I think I can finish.
Okay. Go ahead.
Because I just want to state an open problem.
Okay.
Okay. Let's do it. It will take time.
Okay, let's take a break and we go to CS26. I have booked the room. I don't know how the recording and all will be, but hopefully do well.